Hello everyone. In this video we're going to talk about exponential growth and exponential functions. Exponential growth is an incredibly important concept in the sciences. It describes how things that reproduce themselves, how quickly they grow. So this is seen when we look at the rate at which bacteria grow. They can reproduce asexually, splitting one of themselves into two, and then each one of those can split themselves into two more, and each one of those can split into two more. And so this is exponential growth, the growth of these bacteria. Of course, we know that viruses spread this way. We know the rate at which diseases spread through a population works this way. We also have the similar thing, but in the reverse, the rate at which some things can decay, and this is seen in radioactive decay. You take a radioactive isotope, and the rate at which it decays is described by an exponential function. So let's take a look at an example where we're going to relate exponential functions to linear functions, just to kind of get a comparison. All right, so let's start with an example of linear growth. This is an example where bubbles are going to be forming, and they're going to be forming at a constant rate. And this gives rise to a linear model of growth. All right, so what we're starting with here is 0 bubbles. At time 0, say the time is measured in minutes here, after 0 minutes we have no bubbles. But after a single minute, 5 bubbles are going to form. And after another minute, 5 more bubbles are going to form. So now we have 10 bubbles. After another minute, 5 more bubbles are going to form. The bubbles are forming at a constant rate, 5 bubbles per minute. After 4 minutes, we have 20 bubbles. After 5 minutes, we have 25. 6 minutes, we have 30 bubbles. 7 minutes, we have 35. And you can see what's happening here. Every minute, we're adding 5 bubbles. All right, so let's try to find the linear model that describes the bubble growth. All right, so let's go back down to time 0 here. All right, and what we're going to do is we're going to make a table of values. On the left-hand side of the table, I'm going to have time, and on the right-hand side of the table, I'm going to have, let's say, b of t, the number of bubbles at time t. Okay, so at time 0, we have 0 bubbles. All right, let's advance to time 1. At time 1, we have 5 bubbles. Time 2, 10 bubbles. Time 3, 15 bubbles. Time 4, 20 bubbles. Time 5, we have 25. Bye. Time 6, we have 30. And at time 7, we have 35. And so what I'd like to do is find a formula that takes us from any time t to the amount of bubbles at time t. That'll be the expression that we have for b of t. Well, how do I convert from the numbers on the left to the right? What's my function that gets me from the left column to the right column? Well, it's not too hard to see that all I have to do is take the number on the left and multiply it by 5. So my function is just 5t. So we can say that b of t is just 5 times t. That's my linear function. And you can see it's a linear function with slope 5. Next, we're going to look at exponential growth. And I mentioned that exponential growth is modeled by bacteria, for instance. And so here we have one little bacterium. We have at time 0 a single bacterium. Now, what the bacteria do is every minute they double, because they can reproduce themselves. They can split themselves into another bacterium, and so then you have twice as many bacteria. So after 1 minute, what's going to happen here is we're going to have 2 bacteria. And after another minute, they're going to each double, so now we're going to have 4 bacteria. After another minute, we're going to have 8 bacteria. 1 more minute, they're all going to double, so now we have 16. After another minute, we've got 32. After another minute, 64. After another minute, 128. You can see they're multiplying quite rapidly right now. Every minute, they are doubling. So let's do what we did before and write down a model for this growth. So I'm going to make 2 columns, just like we did before. Time on the left. And now my function is going to model the amount of bacteria. Let's use lowercase b for this. So it'll be bacteria at time t. All right, so at time 0, we have 1. At time 1, we have 2. At time 2, we have 4. At time 3, we have 8. Time 4, we have 16. At time 5, we have 32. Time 6, we have 64 bacteria. And at time 7, we have 128. So the question is, at any time t, how do I compute the amount of bacteria that I have here? Well, one thing I can see that's happening is if I go down the right column, I'm just multiplying each number by 2 to get to the next row. So here I've multiplied by 2 once. Here I've multiplied by 2 twice. Here I've multiplied by 2 3 times, 4 times, 5 times. So you can see that the left column is the number of times I've multiplied by 2. So if you want to describe that mathematically, that's of course when we use exponents. So we can see that the formula here is 2 to the power t. And so that's our exponential function. It would be 2 to the t. Note how that's different than the linear function we had before, which was 5 times t. T was not in the exponent. Now we have t in the exponent. And that's what makes this an exponential function. Now let's take a look at a graph of what's going on. I'd like to compare the linear function and the exponential function side by side. So what we have in this graph is we have the red dot displaying the amount of bacteria we have at time 0. So at time 0 we have 1 bacterium. And the blue dot is describing the number of bubbles we have at time 0. So at time 0 we have 0 bubbles. And as we increase time, so let's make time equal to 1, we see that the amount of bacteria has doubled, so now we have 2 bacteria. And the number of bubbles has increased by 5, so now we have 5 bubbles. If I increase time again, the number of bacteria have doubled again, so now we have 4. So at time 2, we have 4 bacteria. And at time 2, the number of bubbles has increased by 5 again, so we have 10 bubbles. Now let me zoom out a little bit. All right, so I've zoomed out a little bit. Let's go to time 3. At time 3, the number of bacteria have doubled again, and the number of bubbles have increased by 5. At time 4, the number of bacteria have doubled again, and the number of bubbles have again increased by 5. Now at time 5, this is where something interesting happens. Notice the number of bacteria have doubled, but they have also overtaken the number of bubbles. And if I go to time 6, now I'm going off the chart. Let me zoom out once more. Okay, at time 6, we can see we have 64 bacteria, only 30 bubbles. And if I go to time 7, the last time we recorded, I see we actually have 128 bacteria, only 35 bubbles. So while the bubbles were growing faster than the bacteria early on, the bacteria quickly overtook the bubbles. And it didn't take long for that to happen, only about 4.5 minutes. And you can just imagine if we were to let this run for an hour, the amount of bubbles compared to the amount of bacteria would just be, it would be such a difference that the number of bubbles would just be insignificant in comparison. And this is a property of exponential functions. Exponential functions grow much, much faster than linear functions given enough time. They will always overtake a linear function. And it's not only that, but also polynomials. An exponential function will grow faster than any polynomial. You can make the most extreme polynomial you want, x to the power 1000. Doesn't matter, an exponential function will overtake that polynomial given enough time. So whenever we're dealing with exponential functions, and if people talk about things being having exponential growth, that's something you really, really want to take seriously.